Myron Ismenhard is trying to get a heater working in his aerodynamics. And I gather he wants a superheater. Not only does he want the superheater to work, but an Evans Spocker to work in parallel with it. We had built this specifically to add single wire CAN to the CAN-DUI shield. And that's kind of important to use the Evans Spocker heater, which so far there's not been much demand for anyway, and maybe just something to entertain me. The other part is largely to entertain me, and that is the discovery that I will share with you, that very few people know, that the Tesla supercharger network is virtually chattable with a VIN number and kind of a neat feature where it can reset at any time during the charge process and redo the negotiation in case somebody else plugs in or a cloud goes over the solar panels and its ability changes. Beyond that, it is basically Chatamo on a single wire CAN at 33.3 kbps. And so we have added that here. There's your ground single wire CAN. These two pins are for a load resistor that shouldn't be there, but Paulo was sure we would want to play with that a lot. I didn't, but in any event, we added a single wire CAN transceiver that's really quite a neat chip, and it works on the same output as CAN 0,
CAN 1.
CAN 1, this one.
It's actually,
That one.
that's CAN 1, that's CAN 0. I know it looks backwards.
But this is the one you changed,
No,
right?
that one.
No.
This one.
Yep.
Okay.
Those are the two that.
And they are in conflict. It turns out that the single wire CAN transceiver does not interfere with CAN 1, but CAN 1 does interfere with the single wire transceiver. And so my failure to get the Evans Spocker working with this board is because we had no single wire CAN, and to get it you have to remove this chip. Simply desolder it and remove it from the board. So we'll be redoing that. Steve West here this morning?
There you go.
Not yet.
He's waiting for a load to come out of the dryer.
Didn't make the call, huh? All right, so we won't need to, we'll deal with that later. So that's the deal, but this shield relies on the existence of an Arduino library called CAN-DUI. And as I mentioned yesterday, that was actually the nexus in the universe where Collin, Jitter, and Jack Rickard collided, although it was over the Machina board at the time. It's since evolved. I have contributed nothing to this, by the way. It's entirely Collin's work. And it's, I think, a brilliant work that he doesn't even realize the import of at this point. Someday he will. CAN-DUI does work with it, and it works with our EVTV DUI board, and it works with the JevCube, but it's actually not very specific to anything we're doing. He's already made it where it can be used on a number of things. I think he's working on TNC or something.
Yeah, I'm working on that too.
And so there's a, that will be the default CAN library, and eventually I think it'll be in the core of Arduino. And so we want to talk about that today. I'm going to kind of set this up with vague generalizations in arm waving, which I'm also good at, and say that the Arduino processor and its integrated design environment, or IDE, which is so easy to download and install and use that I've got old men grabbing it to be able to have a terminal program in Windows. They're never going to program anything, but they need a terminal. And that was one of the reasons we selected Arduino as our ecosphere to operate in for all these projects. So it's a language originally called processing that resembles, to me, nothing so much as C++ without the standard STL library. And indeed, there's the development of a whole lot of libraries for it, for usually specific hardware, but also sometimes to take advantage of hardware features in the Arduino itself. The DUI has, for example, 3 clocks or 3 timers, and each of those timers can have 3 interrupts. And so we have 9 different interrupts we can use, and we basically took good advantage of those for the JevQ to build probably the clunkiest real-time operating system ever built, but it's fairly effective. And that's done with a library, in that case, done by a guy in Brazil. And that's why, again, the ecosphere of Arduino was what was attractive, not the hardware or any specific processor. So you have a language that looks like C++ syntax, and indeed is object-oriented. And you can add a library. What is a library? That's some other software that's pulled in and compiled at compile time and added to your program. And the reason you want to do that is because it extends your language and gives you new commands you didn't know you had. And in a lot of cases you don't know how they work. But you can include them in your program and do remarkable things. And they have hundreds of libraries, literally. And there's a whole series of them that you get with the Arduino IDE, and then literally hundreds that you usually find on GitHub. In this case, github.com/Collin80. And so those give you new commands, and I would say new object. And so we can make an object, create an object. We usually refer to that as instantiate an object, simply by giving it a name. And the object here is CANFrame, and so you have a declaration CANFrame and a name. Jack's a silly little CANFrame would do fine, but it'd be a lot of typing. Or you could call it C1, that would work just as well. And then Collin's library has commands that will operate on that, like begin, or set WatchFor, or a whole lot of things. And so if you don't know how those commands work, it can be a little difficult to use the library. Typically, people who write libraries write an MD file that contains a 25-word or less description of exactly how to use it, that even the author can't really parse through and do anything with. And to make up for that lack of documentation, they do 2 or 3 example programs to illustrate it, which shows you about 10% of the commands. And that's unfortunately the state of the documentation for libraries. In our book for this, I have about half of CanDUI documented, and some of it in error. But we're working on it. Even better, today we have the author of CanDUI, Mr. Collin Jitter, and he's going to walk you through why you would want one and how you would use one if you did have a device to use this library. Would you all please give a warm welcome to Collin Jitter. Hello, setup. Fumble, fumble, fumble. Better. Behind the speaker's good, in front of it's not so good. You're not going to like me out there in front.
Posting? All right.
We're going to go through a quick slideshow. I've also got one of the things he mentioned. Most libraries have a couple of example files. In DoCan, there actually is probably about 8 examples. So there's quite a bit of documentation on this library in the examples, and I'll go through a couple of them also to kind of better show. I'd like to do a general overview first. Just, you don't really need to remember these details so much because the library handles it all for you, but it's good to keep in mind. The hardware in the SAM3X processor has 8 mailboxes per CAN bus hardware. A mailbox is a place where a message can come into from the CAN bus or exit the processor onto the CAN bus. And each mailbox is set either as a receive or a transmit. So it's kind of, in the real world, you use your same mailbox for sending and receiving mail. You do not do that here. 8 mailboxes, they either are receive mailboxes or transmit mailboxes, and you set them at the start of the program. If you don't do anything, the library sets them to 7 receive and 1 transmit, because normally, especially with the sniffing and everything, what you're doing is receiving frames. You're not doing a lot of sending. So it defaults to mostly trying to receive frames. Everything is interrupt driven. That's just kind of a reference point. You don't really need to worry about that much. But the bottom line here is there are 32 receive buffers and 16 transmit buffers. So you don't have to do anything. The program will store all that traffic, even if your computer hasn't had a chance to receive them yet. They're stored in the background for you. So it's kind of just a convenience feature. First thing you would need to do is access the CAN bus. And Jack had mentioned about instantiating objects or having objects that are available for you. If you're used to doing Arduino programming at all, there's objects like serial that he had showed, serial USB, serial 2, various objects like that that you can use to access serial ports. In this library, the 2 CAN buses are either called all uppercase CAN or all uppercase CAN 2, or you can call this one CAN 0 and CAN 1. These were added later on, and they're more or less the preferred names. It looks a little bit more like the way that Arduino normally names objects. Like I said, you have serial and serial 1, and they're named with only an uppercase letter and then lowercase. So I'll show some examples of how that works, but those objects are made for you. Then to use the CAN bus, you'd have to use begin. I believe Jack had showed that in one of his sketches. The begin function takes speed and enable pin. Unfortunately, you do have to set the enable pin for a lot of boards, and it's going to be different for every board that you're using. If you don't need an enable pin, it can be set to 255. But an example here could be, you'd say begin 250,000 and enable pin 50, which on the EVTV DUI board and the CAN-Do 2 boards, enable pin 50 is the first CAN bus. So the examples, I believe, do show that. But that's how you would start the CAN bus. Once that has happened, everything else kind of magically happens for you in the background. As soon as you call begin, it will start receiving traffic. Filtering is the big thing Jack showed, I believe, yesterday. He had used this function, setRx filter. When you first start up, you don't have any filters set. You kind of have to set what messages you were hoping to receive. The easiest approach here is this WatchFor function with no parameters. That just lets you watch for everything. You don't have to ask for any different frames or anything. But a lot of times you're only looking for a specific couple of frames that you really want to know about. For that, you can easily just use WatchFor and the ID you're looking for, or WatchFor range. I kind of like this one. If you know that you care about messages 600 through 620, you can put WatchFor range 600, 620, and it will accept all frames from 600 to 620 automatically for you. One of the things that Jack said that I would cover today. It's kind of a tricky thing. When you have ID and mask here, you're asking for the ID and the mask. What will happen is when you get a message into your board, let's say that message 745 came in. If you set a mask of 7F0, what will happen is it will take 745 and 7F0, which is a logical operator, and that turns the 7F0. What this means is when you have a 0 here, it chops this value 5 off and lets only 740 through. Now when the filter ID is 740, it matches. So this mask is just a way to cut information away so that you only match a specific range of IDs. This is kind of a more advanced way to do this, which is why I like this function. It doesn't require you to think about masks, which can be kind of a complicated subject. With this, I would kind of recommend WatchFor range. It's the easiest approach. If you need IDs from 400 to 600, you can just put 400 and 600 and watch for them all. It's a lot easier. The can frame structure that he mentioned has all of these various pieces in it. You've seen before the can frame, you can set the ID of the frame. If it's coming in, it'll tell you the ID that came in. If it's going out, it's the ID to send on. Family ID is kind of an advanced subject that's really not used. He had mentioned RTR, remote transmission request. That actually has been deprecated since probably the mid-90s. Virtually every CAN bus library has it. Nobody uses it, so I would think you probably want to ignore that as well. Priority is not used very often, but if you're sending multiple frames and you really know that some of them are important, you can set the priority higher, and those frames will have preference and be sent out first so that you know that those frames got out, even if the bus is very highly loaded. It's a little bit weird in that priority is backwards. If you set a priority of 15, that is the lowest priority, and 0 is the highest. But normally you don't have to deal with that. Extended, Jack had talked about 11-bit and 29-bit IDs. Almost everything uses 11-bit IDs and standard. But sometimes you have to set that if you're using extended frames, which do happen occasionally. The length, you can set the number of data bytes that you actually want to use. And then this is kind of a tricky one, this bytes union with data. I'll cover that in a second. But really, if you see this can frame struct, the only things you probably care about, the ID, the length, and the data. Most everything else is kind of very rarely used. Here is the structure of data, this bytes union. It allows you to specify data in a variety of ways. I think he had used bytes before, so we have data.bytes, and you can access the 8 individual bytes that are in the frame. But what can be easier if you know you're storing 16-bit values, you can use S0 through S3 and store the 16-bit value in one shot. Then you don't have to worry about how you're going to break it up. He had used high and low to break up a 16-bit value into bytes. You don't have to do that if you use these S's. You can just directly store a 16-bit value directly into data. Same thing with 32-bit values. You have low and high. These are the first 4 bytes and the last 4 bytes. So you can store a 32-bit value without having to worry about how to break it up into 4. For here, you'd have to break it into 4 different bytes, but you don't have to do that if you use this. Or if you want to store a 64-bit value all at once, you can just use values. So there's a variety of different ways to store data, and this is just a convenience so that you can easily store and retrieve 32-bit, 16-bit, and 64-bit values without having to use extra functions.
Can I point out that Arduino IDE uses a 32-bit integer. We often specify 8 bits or 16 bits, but if you just specify an integer, it's a 32-bit value. You can stuff it right in the 32-bit thing and take it out the other end, and it's as it ever was.
Yeah, so that's a little easier than trying to break that up because it is 32-bit native. Now, Jack does not use polling-driven reception because it is a bigger pain in the butt to do. But if you look at the source code for GVRET, I actually have done polling-driven reception. So that'll kind of be a reference. And some of the examples that I'll show you also use this. Now, the whole library is interrupt-driven in the background, so this is kind of a little misnamed, perhaps. But this allows you to ask for frames when you're ready. There's two approaches in this library to receiving frames, the polling-driven approach and the callback approach that he likes.
Is there any performance difference between the two?
Not really. The only reason that you really would use one over the other is if you want to be sure of the time frame when you're processing the information. With the callback approach, you could be in the middle of the sketch doing something else. When a frame comes in, it will jump out from what you were doing and go to the callback and process the CAN bus frame. If you don't want your sketch to constantly be bouncing back and forth with the callbacks, you can just do polling driven, which is why I did it in GVRET. I wanted to process the frames only in one section and then send them out the serial port, which might be a little bit more efficient. With GVRET, I was trying to make sure that I could do 8,000 or 9,000 frames a second. So probably nobody else is ever going to need that kind of level of performance. But
So if we're loading up a buffer and then sending
yeah, I'm just loading up a buffer and blasting it out the serial port. So that's why I use the polling approach. With polling, what you would do is use this RX available function that returns true or false. If that returns true, then that 32 position buffer that I talked about before has at least one frame in it, and maybe up to 32. The alternative approach is to use available, which will tell you the actual number of waiting frames, but normally nobody really cares. There are two functions that do the exact same thing. The old function that I left in just for compatibility is getRxBuff, but that's kind of a long, cumbersome name, so you can just use read. And inside the read here, you just pass, when you make a CAN frame variable, you just pass the name of the variable in there and it will fill it out for you. This might look a little weird. You see the little ampersand there? It means reference, but basically what it means is that if you pass it the name of a variable, it will fill that variable out for you. So you can see an example here. If you just set up your frame, my frame, ask on the first CAN bus there, CAN 0, if a frame's available, you're reading it in. So that's how you can ask for frames if they're available and kind of pull for them and get the frame when you're ready to receive it. The alternative approach that Jack likes is to use callbacks, where you create a function with a name here, void, and your function takes CAN frame pointer to a frame, and you set up that method will accept callbacks when you ask for them. You can set a callback here on mailboxes. There's 8 mailboxes, and you can set a callback on any of them. It would be kind of a crazy idea to set a callback on a transmit mailbox. It will let you do it, but nothing will happen. So really, you're kind of sticking here with your receive mailboxes. You can set a general callback as well. If you did not set a callback on a mailbox, let's say you have the 7 receive mailboxes, but you only set specific callbacks for 2 of them, set general callback will make a callback for the other 5 that don't have specific mailbox callbacks. And I think that he had shown in his sketch, he only set general callback. I like to do that a lot too. If you don't care what mailbox it came in on, then there's no reason to set up a ton of mailbox specific callbacks for no reason. There's an alternative syntax. I added attach can interrupt here just because Arduino has attach interrupt as a function, so this kind of makes it a little more harmonized with the Arduino naming syntax. It's exactly like these other two functions up here, attach can interrupt with just the callback mailbox is just the same as set general callback, and attach can interrupt with the mailbox specifically stated is the same as set callback. And you can use a hybrid approach. You can still use the polling functions if you didn't set up mailboxes, or if you didn't set up callbacks, the polling functions will still work. So if you really wanted to get tricky, you could say set a callback on mailbox 0, get a callback only for that mailbox, and all the rest of your frames would come through polling. Don't know why you would want to do that, but it does work, and I've tested it.
Let me clarify here a little later. He'll talk about filters, but this is a way to make a function for a specific message ID. When this ID comes in, this function is where it gets routed. If you get a different message ID, it goes to a different function. You can have a function for each message ID you want, and then a function just
that is something I kind of accidentally glossed over. I had said in the callbacks you could set a callback on a mailbox, and for the filters, when I covered it, you can see you can set an RX filter on a specific mailbox. So if you knew that you wanted, say, to accept ID 600, and you tell it that you want ID 600 on mailbox 0, then when you do a callback on mailbox 0, you'll get only the stuff that matched this filter. And if you filtered, say, for only ID 600, that mailbox will only get frame 600, and you can use that to do specific functions that depend on that ID. You can kind of narrow it down that way so that the callback, say if this callback, you might register one that deals with the motor inverter, and that mailbox accepts only messages from the inverter, then you know when you do this callback function that you're writing that you're going to handle inverter traffic, and that can kind of compartmentalize things a little bit. The last thing to go over here is sending frames. There's really only one function, just send frame, and the can frame that you had set up. As an example, you can make a variable myFrame out of the can frame structure there, set its ID to 100, set its length to 1. As I mentioned before, the data member here has all those various things. You can access it by bytes, 16-bit, 32-bit. So I'm just saying that the first byte here is 20, and then send it right off. Use the reference to the variable that you made here. Sending it on can 0, which is the first CAN bus, just send it right off. So that's fairly easy to do. If you needed to set the priority, you could do myFrame.priority equals 4, or whatever the priority needed to be. As a kind of advanced thing, there is a function here, set number of TX boxes. I mentioned that RX, or the received boxes, were set to 7 by default, and the transmissions boxes were set to 1 by default. If you know you're going to transmit a lot, you can set aside more of the mailboxes for transmission. You can only really send one thing at a time anyway, and there's a 16 position buffer, but with very high loads, I think in JevQ, Michael Neuweiler, who was one of the guys working on kind of an alternate version of it, had found that he was sending so much traffic that he could overcome the 16 position buffer. And one of the ways that he got around that was to set up to 3 transmission mailboxes so that he could more quickly send traffic out of the bus. It's probably not something you'll ever have to deal with unless you're using the CAN bus to a very high load.
Now, you don't need to deal with the 3 boxes once you set them.
Yeah, you don't ever deal with them.
Or whatever.
This is all hidden. This send frame, I put here, it will attempt to immediately send on a free mailbox. If you have one mailbox here, and let's say you send 2 things very rapidly, the first one will immediately go into this open transmission box and start to be sent. When you try to send the second one, this box is still busy sending the frames, so what will happen is it'll go into that 16 position buffer I talked about, and you don't have to worry about that at all. All these things happened in the background. If you had 3 boxes and you sent 4 frames, 3 of them would immediately go into the 3 boxes you set up. You don't have to do anything to make it do that. The 4th one would then go into a buffer. When one of the 3 boxes gets done sending, it'll automatically come back here, see that the buffer has something in it, and load itself back up. Everything happens for you in the background. So as far as you're concerned, really, you send a frame and it's gone. The library handles all the nasty details in the background.
So we need to send faster, just provision another transmit box. But it's shared with the receive box. Now you have one less slot.
Yeah,
for the
it
receive.
removes it from the receive side. As I mentioned, there are a lot of examples in the EVCON library. I'll show you sending test. Of course, it came on the other screen here. Once again, to use this library, you just include it, docan.h. If you've got the library in your correct location for the IDE, it will do that. We use this a lot in the sketches just so that you can always use serial. Most all these ports, the EVTV DUI only has serial USB, so using serial ordinarily wouldn't work. We set serial.begin here to set up the serial port at a quick speed. Actually, when you're using serial USB, this begin command doesn't really matter at all because serial USB is technically about 10 million here, and it's hard-coded. So really what you set here is totally meaningless for serial USB, but if you ever did use a board where you're using the serial port, you would have to set something there. As I said before, when you use the begin function to set your speed, we're kind of using a cheat here. Can underscore BPS underscore has a bunch of defines for the various speeds that you're likely to use. There's, I think, 50. So you can set 50K, 100K, 125K, 250K, 500K, and 1M are all defined as common speeds. Or you can write it outright, which actually would have been less characters. So you could just say 250,000 here. But those set up the speeds. We're setting both CAN buses here for 250,000 as the speed.
Collin, could you go to a bigger font here? Would that be too much
Oh.
trouble? We can't see anything here.
Can't you see it? Yeah, I thought I had set up a bigger font. Maybe it dropped back on me.
Can you control scroll with this?
You can't in this IDE, unfortunately.
Okay. That'd be nice.
Is that a little better? And then, as I had covered before, using WatchFor with nothing in it watches for absolutely everything. So we're saying here that the first CAN bus, we're going to watch for all traffic and don't really care what we're looking for. I've got a send data function here just to kind of show the various ways that you can send data. I've created a CAN frame variable. We're setting the ID to, in hexadecimal, 400, saying that this is not an extended frame. The priority will be 4. which is a fairly high priority. And then just to show us some various ways to send the data, you can set data.s0 for the very first 16-bit value. And I'm setting it to feed. And then those would be byte 0 and 1. So then I'm setting byte 2 to DD, byte 3 to 55. And then demonstrating how to use a 32-bit value would be data.high and setting it to dead beef. Yeah, we have feed and dead beef. I like to write things in hexadecimal that make English just kind of fun to do. So then, as mentioned, you can just say that on can 0, we're going to send the frame and use the name of the frame that we set up there. So just set it to outgoing, and the frame will be sent off. Here's another example in loop of how to do polling mode. Set up a place to get our incoming messages, the incoming variable. Ask if can 0 has any messages available. If it does, we'll read that message in with incoming. Immediately send it back out can bus 1. So this is just kind of a forwarding type sketch where anything that comes in one, or in the first one, will go out the second one. And then here,
And that's pretty cool because they can be on 2 different speeds.
yeah, we could have set, I could have set different speeds if we wanted.
Yeah, and then you're kind of bridging from one CAN bus to the next.
You could also, in between sending it back out, you could chew it up and process.
Yeah, there's actually an example. I tried to write as many examples as possible. There's an example of how to do a traffic modifier.
I didn't mean to divert you.
Well, that's pretty much the end of this sketch anyway. I did the same thing as up here. Now, if anything comes in on can 1, we'll flip it back around and send it off on can 0. So this is bidirectional forwarding. And then I set here, set up the time. There was a static variable. Static variables are a way to cheat and make global variables without using evil global variables. So a static variable in this loop here will keep its value in between cycles of the loop. So I'd set last time defaulting to 0, but I'm using this here, millis minus last time if it's more than 1,000. So basically every 1 second, we'll send data and go up to the method that I had made up above to send out the data in the various patterns that you can send it out in. So that's one example.
So how many lines of code do you have total there, Colin?
That's 52.
Yeah, this is, you hear about these millions of lines of code sets. You can do a lot with these little boards and 300 lines of code. This is not writing the book of life or anything here.
Here was what I had mentioned, a traffic modifier sketch.
Exactly.
And this is also, this was written before the WatchFor function. Some of these examples are kind of old. This would show you how to set up to accept any frame you want. It's kind of the manual way. This is what WatchFor looks like internally, if anybody was curious. That's basically how you set up an open filter that accepts everything. Now, this has a function to print out all the frames that come in. Kind of Arduino has nice methods here that can do a lot for you. So I don't have to deal with how to turn the frame ID into hex. I can just tell Arduino to print the frame ID in hex, and it will make the character string for me. Print the frame length. Doesn't really need to be in hex because it's only 0 to 8. And then I'm sending out all the frame data, each byte in hexadecimal as well. But the print method there is very handy. It will format numbers for you automatically. So that just prints out all of the traffic that's coming in. I've got this modify frame method here. This shows you how to kind of take input and modify it so you can send it back out. We're switching here on the ID just to grab different IDs. If an ID of hex 200 comes in, what we're going to do is take byte 0, add 10 in hex or 16 to it, and store it back in there. We're going to take byte 3 and set it to DE. If a frame with ID 300 comes in, we're going to set byte 0 to the combined total between byte 1 and byte 2. And if frame 320 comes in, we'll 0 out byte 7 and set byte 5 to FF. So a little while later in the sketch, we see where that's called. If can 0 has some messages available, we'll read them in, send them to ModifiedFrame, which sends the reference to this frame that we just read. ModifiedFrame up there will, when we go back up, if the incoming frame were any of these IDs, 200, 300, or 320, the data in it will be modified. And then we send it back out the other CAN bus. So this would be a way, if you wanted to modify traffic that was coming in and resend it. This is kind of an example sketch. A nice, easy thing you can do here. Let's say that you have an inverter, and it's getting messages from an ECU, but the ECU isn't commanding as much power as you want. You could use a sketch like this to read the incoming message from the ECU, cut the CAN bus line so that the inverter is on CAN 1, the ECU is on CAN 0, so you read in the message that the ECU is sending to the inverter, modify it here to up the power, send it back out to the motor controller. And you could actually hack your car that way.
Or kind of a man in the middle, that's be the easiest.
Yeah, you're playing a man-in-the-middle attack against the car.
It's sending something to your fuel gauge, and you just get what it's sending and replace it with what you want, and it shows up on your
So this is only 83 lines now to the end, and that shows, in 83 lines you could write a sketch that hacks your motor controller, makes your fuel gauge work differently, anything you want to do.
Create a ballet mode.
Yeah, create a ballet mode, anything that you want. All that you would be doing is changing this modify frame method right here to grab the IDs that you need to change the data that you need to change, and that's it. You can man-in-the-middle attack pretty much anything.
And the time delay between when you receive it and when you send the modified one is nothing.
Microseconds. The processor in here is 84 megahertz, and it can do pretty much one instruction per clock tick. So this whole modify sketch is probably never going to take more than 40 or 50 instructions at most, so that's still less than a microsecond, less than a millionth of a second to run through that modify frame method and then spit it back out. It's probably a few millionths of a second between the time that you get it and the time you can start sending it back out.
So you'd just be cutting the CAN line then and sending
Yeah,
the
you could.
signal.
Basically, you'd be cutting the CAN line to the object that you want to modify, and then you put, say, a can-do 2 board on both sides,
Yeah.
so
okay.
that it's
I got you.
handling in between.
And both of them at the same speed.
Right.
Yeah, both at the same speed probably there. Though if you wanted to be tricky, you could do different speeds, but I don't know where that might be.
So if you know you got
Well,
more.
actually, you
more
could use it as a
motor,
gateway too. If you had a device that was, say, 250,000 speed, and you needed to use it on a network that was 500,000 speed,
Right.
you could do something like this
You need an engine swap.
to translate the speeds for that device.
So if you know you got a motor and a controller that's got more in it than what they're giving it, you can help it a little.
Yeah. In fact, I want to do that. I have a couple of Think City cars. It was from the Think Corporation in Norway. And the car has been a dog. It didn't accelerate very quickly at all. And I'm sure the inverter has more guts than what the ECU is telling us. So I really want to cut the CAN lines and do that.
So
Just haven't yet.
Little known fact, but Jeff, you include support for the Think City BMS for any of
Yeah, it does, because now I have 5 Think City battery packs.
When you're the programmer, you can put in anything you want.
That's the whole point.
I'd like to do an example here too. So far, all those examples have used polling mode. Probably a good idea to get callback mode. Here's the same type of print frame method that we had seen before. That's just kind of the same. Here is how callback methods would be constructed. I have got frame in mailbox 0 and takes a pointer to a can frame. And I've got that function up there, print frame. The only difference it was from the previous sketch is that this print frame also accepts which filter was matched, so that I can print out the filter and we can say which mailbox it came in on. So this callback just says we're going to print out the frame when it comes in mailbox 0, and it was mailbox 0. Now, another callback here that was set on mailbox, that we're going to set on mailbox 1. So we print the frame and we say it was set on mailbox 1. Then I had mailbox 3, 4, 5, and a generic one. Here I set up specific filters on each mailbox. On mailbox 0, I'm going to look for a message with ID 2FF00, which obviously it has to be an extended frame because it's a very long address. But we're going to match on this first mailbox, or second mailbox on mailbox 1, we're going to look for 1F000. On mailbox 2, we're going to catch everything else that's set true here, which means every other extended frame will match mailbox 2. Then for standard, I've got a couple of random things. We're going to match 40F as a address, and 7FF for the mask means that we have to match this perfectly. It's going to match that exactly right down to 40F, and no other IDs but that one. For the mailbox number 4, I'm going to match 310, but with the 0 here in the mask, it means it'll match 310, 311, 312, 3E, all the way up through 31F. So that matches 16 addresses will match on that mailbox. Then down here, this shows that you don't always have to set the mailbox explicitly. You can just watch for an ID and a mask, and the mailbox, it'll automatically find a mailbox that's unused. So in this case, I used 0, 1, 2, 3, 4. So it'll automatically use the 5th one. You don't have to set that. The last thing I'm doing is setting up a filter, not specifying the mailbox, but it'll be 6. And that'll match every standard address.
All that makes sense to Collin. This masking with the 7FF, I attempted a explanation in the CanDUI manual of how it's actually an exclusive or something on each bit, and it's not a great write-up, but it might get you there.
Yeah, I mentioned in the filtering, this is all kind of complicated to explain. That's why there is a WatchFor range function. You probably want to use that because you don't have to worry about masks at all. Just WatchFor range, the lower bound range and the higher bound range. So if you say WatchFor range 600, 6FF, you'll accept 256 addresses. You don't have to worry about how to set the masks. The library actually will figure out the mask for you.
Unfortunately, the masks are still quite powerful. You can route, using my method with the interrupts, you can route all 600 messages to one function all 730 anything, 730 through FF, or 730 through 73F to another one, and then the another one by the whole message has to match. So unfortunately, the masking is kind of a cool feature.
Yeah.
And yeah, he's got some easy ways to do it, but the masking is still pretty powerful. And you kind of have to read through the write-up on that in the book to see what's happening at the bit level.
Yeah. So once you go through all the trouble of trying to make all the complicated masks there, you can just set the callbacks. You know, this is at least the easy part. Set a callback for mailbox 0 that we made above, and you're going to use the function name that we made above. And I did that for all of the ones that don't have the open pass-throughs. So mailbox 1, 2, 3, 4, 5, all set the callback to the functions that I made up above that are all named those same things, mailbox, or got frame MB5. And then we have the general callback there, got frame, that's set. Like I said before, you can set the general callback. And then anything that doesn't match these things will automatically go here. So
Now, is that in the program important to have that in any particular order? Can you put the general callback first?
yeah, it's not important to have it in any order at all.
Okay.
I did it in order, just numerically, 0, 1, 2, you know.
I always do it that way,
But yeah.
but it's mostly in my head. I think that was my question. Does it matter?
Well, I think that Jack, a lot of times too, would set the filter and then set the callback and then set the filter and set the callback. That might look a little more clean. That's just a stylistic approach. It totally doesn't matter. As long as you set the filter at some point and set the callback at some point, it will work. So this shows how much easier it can be when you don't have to pull. The loop here has absolutely nothing. You don't have to do any work to get these messages in. Once you set these callbacks, they will get called automatically, and you never have to worry about it again. So kind of a little bit easier approach. It's a little bit harder to set up the callbacks initially, but it's a lot less work eventually because you're not doing anything here. You're just waiting for CAN bus traffic to come in.
They're working in the background kind of thing.
Yeah, it's just working in the background. The library is always interrupt driven, which basically means it works in the background behind your back. So the polling approach let you take a little bit more control over when you actually read the messages, but the library is always reading them behind your back and buffering things up. So you never really have to worry about that. It's always handling the behind the scenes details automatically.
And at 84 megahertz, it's not going to affect your loop at all.
Yeah.
Yeah, there's probably not much time advantage other than the callbacks. It executes when it arrives.
Immediate
With
execution.
the polling, it's when I get around to it, I'll go process CAN messages.
Yeah.
If you have a time-sensitive function, then polling would be the way to do it.
Yeah,
If you don't put jitter into your robots.
If you knew that it was time set, let's say if you're doing a robot or if what you were writing was a motor inverter and you were right in the middle of the motor inverter's main loop, you probably don't want the CAN bus to interrupt you at that point.
Yeah.
So in that case, you would want to use polling because you wouldn't want to have an interruption right during a very critical moment. Say when you were setting the IGBTs and all of a sudden the CAN bus interrupt comes in and delays you for several milliseconds, that would be a bad thing.
You shoot through and blow the whole thing.
So
It's other than that, it's mostly stylistic. The classic C++, you don't use global variables, and I kind of view everything as a state machine that's held in the variables. So when the message comes in, the ultimate thing I'm going to do is change one of those variables based on the message. And so anything else in the program, when it goes to that variable, it's going to have been set for it without anything in between. So this is a stylistic approach, it's how you pose this.
I'm going to cover just one more thing, just kind of as a word of caution. We talk about how the Arduino sketches are technically C++ because they really are, and you can use almost any C++ capability you want to. You can use classes. You can have giant class hierarchies, and in fact, if you look at JevQ, you'll find out that the entire thing is a giant mess of classes. So it is possible to do object-oriented programming, and it's still possible to do object-oriented programming with the DoCan library, but I'm going to tell you you don't want to. At least not if you're going to do callbacks. And the reason is that the callback, you saw when I registered a callback, it required a specific way for the callback to look. You can't do that with a C++ function. If you have a class, your function will not have the correct
Prototype.
That's actually an important point.
Yeah, it won't have the
almost
correct
went crazy trying
signature.
to create an object that used canvas, and Collin finally told me,
So,
I'm sorry, you can't.
If you have a callback that you wanted to have inside of a class, you have to actually use a trampoline function, which is this here. This is a callback that you can actually register with the library that instead of doing something, just calls into the class that I have set up. This is the instantiated, this is the object that I made. And I call the object inside of this trampoline function, because otherwise you can't use callbacks with C++ objects. So I would recommend against that because it really looks silly and it's a lot more difficult to do. So
And it's hard for other people to read.
yeah, and it's hard for other people to read. There's an example, this sketch, Can Snoop CB Trampoline, shows you how to do it, but it looks ugly. So there's an example of how to do it if you have to, but using C++ objects, it will really be a lot easier if you use polling mode and ask for frames when you're ready, because the callbacks look silly.
And he's explained this to me 4 times, and I still don't get it, so
Well, I mean,
you don't want to hear it.
yeah. The fundamental problem is that the callback is not, you're not able to pass in a user parameter. Like,
Yeah.
it's because a C++ class has this concept of this.
Yeah,
And if you don't know what this is, then it doesn't work.
yeah, the problem is that when you register a function that takes one parameter in C++, what it really does is pass this comma and the parameter. You always have an implicit extra parameter to C++ functions that's hidden and you never see. But the compiler sees it and throws a fit when you try to register the callback.
It's like a worm. It's collar.
If you send a message to a destination that doesn't exist, are you ever notified of that, or is
No,
there any feedback?
Nope.
there is no feedback.
No echo.
CAN bus really doesn't have a concept like that of sending to destinations by default. You're basically just, you're always in broadcast mode on CAN bus. You're broadcasting and telling everybody everything all the time.
You're
So-
sending it to the bus.
You don't, yeah, you send it to the bus, you don't know who's reading it. You really can't tell. Everybody on the bus could read it, nobody might read it, and you really don't have any real feedback.
I thought there was a bit that got
There is a bit.
said if
You
at
can
least
tell
one
if
person-
someone read it,
Yeah.
but this library doesn't tell you that.
Mm.
Is that RTR or what?
No, there's an acknowledge bit. When you send a frame and it comes out, the sender sends an acknowledge bit that's recessive.
Mhm.
And if anybody reads the message, they'll pull the line down to dominant.
Oh, okay.
And then you can know that it was acknowledged.
They will always, the hardware will always acknowledge it. You don't know if anybody actually is doing anything.
Yeah,
about it.
if somebody's hardware accepted it, in order to accept a frame, it would have to pass through one of the filters.
Okay.
So if your filters are set wrong, and everybody's filters aren't set to accept a message, the acknowledge bit will never be set. And you could, in theory, figure that out, but the library doesn't have that capability right now. If
Plus, if
anybody
you were-
accepts it, the acknowledge bit will be set.
Plus, if you had a wiring fault and it just wasn't, there was nobody on the bus
Yeah,
that could see you, then it will also not get set.
If you
yeah,
have a wiring fault, the act will never get set, and CAN hardware will retry.
yeah.
Uh,
Technically, the CAN bus hardware on this has the capability of setting whether you retry or not. It's set by default to retry forever. But it will keep trying forever if the acknowledge bit never gets set.
The other thing about the CAN bus is, just like you have no idea who's listening, you actually technically have no idea who's sending.
Yeah, that's actually why hacking is so effective on the CAN bus. Because you can send whatever message you want. I can pretend to be the ECU when I connect an extra board up. Nobody knows the difference because there is no real sender ID. It's all broadcast traffic that has no real point of origin or destination.
Now, the corollary to that is it can be very difficult to tell reading CAN bus traffic and the hell it's coming from.
Yep.
Yeah, that is also difficult.
You have to-
You're guessing a lot of times who's sending what.
So you're saying there's no ID in the message that says who sent it?
Well,
Well,
in J1939, there's higher level protocols over top of CAN bus that build on it. Something like J1939 does tell you the sender and the receiver, except that you can lie.
yeah, if
So-
everybody's playing nice, then yes. If somebody is being a bad actor and you're hacking, I don't know.
So yeah, you
But
can
what if
set
that's
that the sender is so-and-so. But you can lie about it, and you can say that you're whoever you want.
CAN buses are entirely built on trust.
Yeah, there is no real concept of security on a CAN bus. It's a real trust and a broadcast type of system.
I don't know how to do this. You've got one data point to compare. I've used some other shields in order to use some of the 8-bit Arduino type stuff, and you can't imagine how rude it is. Could you throw up your CPP and just please don't walk us through it, just to kind of show what all he's done here. It's a lot of stuff.
The file for what?
CPP for GUI CAN.
Oh, for DUICAN?
It's hard to even read. It's a marvelous piece of work, and with these callbacks and the polling and the filters, it's just, there's nothing anybody's doing in CAN you can't do with this library that I know of. And in precious few lines of code, 30, 50 lines. I added a function to GenQ to read by CAN the outputs, or to set by CAN the outputs in about 4 lines. Within a big CAN bus processor anyway.
One thing while he's pulling this up, he was mentioning the mailboxes and the filtering on them. That is likely the reason why on the Tesla you see a whole bunch of retransmissions of the same data, is because little old microcontroller doing one focused task has its mailboxes, and it really only wants to listen to a message to get everything it wants. And so somebody else is shuffling data around.
Right,
So that
right.
the ABS controller can listen to a message and make sure you don't run into that tree.
After a while, you kind of get in the mind of a guy that's doing this, and some guys like to just send a lot of message with a lot of empty space in it, reserved for future use. And other guys, it's like, I got 8 bits, how much of the universe can I get in?
So this is the source code for DUCAN. It's a lot more complicated than the example sketches. Like this is the way to calculate the baud rate divisors and such. That's why it's nice to actually have a library, because you really only want to have to do all this once.
Preferably get somebody
So how
else.
many lines is Dewey Can CP?
1272.
That's 1,272 lines of shit you don't never have to do.
So once again,
That sounds like a plan.
To the can.
you know, because the DoCan library is a C++ class, that I have the same type of trampoline functions in there for interrupts. And all this mess is what the interrupt handler looks like.
Are you saying static methods can't be interrupt handlers either?
Static methods, I believe, can.
Methods cannot, static methods can, functions can. There's
Yeah, if
subtle
you wanted to
differences.
make your method static, but then you'd lose all access to the other class members.
Of course.
So, yeah, you could do it with static members if you want.
But you could hide your trampolining function as a static method.
Yeah, you could do that.
Trampoline into your actual method.
Yeah, this is the source code for DoCan. Kind of heavily tied into the way that the processor works.
Yeah, there's nothing close out there. Or for the other processors. Questions?
Just sort of thinking about practical examples of where you could use this. I've got an instrument cluster in my car which has got a tack and a fuel gauge and things, and I can fairly readily calculate what I'd like them to be. I want to use, say, the tack for amps and the fuel gauge for state of charge. I plan to do that by essentially frigging the inputs to the original sensors. But if I understand what you're saying, I could, in principle, take the CAN wires that are going into the instrument cluster, shove a Dewey in between the two of them, and if I can figure out what the CAN messages are to the instrument cluster, which I think I can, because I've got a cheat sheet, then I could drive the whole thing that way.
Yeah, if the only reason to cut the lines would be if there's some reason that the other side can't get the raw data that was on the first side. In your case, if nobody was driving the instrument gauge in the first place, you could still you wouldn't have to cut the lines, you could just put the board on that same CAN bus and read in data that's on the CAN bus and inject some extra messages into the CAN bus for the gauges.
Well, I'm thinking like the fuel gauge, for example. There's a resistor in the tank, and that's presumably sending a value, or the ECU is getting a value, sending it into a CAN bus message, which is sending to the instrument cluster.
Yeah.
So presumably the ECU is sending something. So if I intercepted that and sent a different one,
Yeah.
is the...
Yeah, in that case, you probably would cut the lines because the ECU is busy sending the wrong data.
Yes.
Unless you're sending it after.
However, that said, John, as a practical matter, if you note when it sends it and immediately send one with some different data,
Yeah, you
your
might be able to
cluster's
override
probably
it.
going to take yours.
Well, that sounds like it might be worth having a go at, just for interest.
It could do
You know your dash cluster's already CAN capable, right?
Yes,
Yeah.
yes.
It's a matter of divining which messages. And,
I think I've got a cheat sheet for that, so I haven't been able to make sense of it.
Well, there again, if you're sniffing the thing, you could actually take the sender out of the tank and raise and lower it to see which variable's going crazy.
Yes,
There's no master on Canvas.
That's what the reverse engineering is about.
yeah.
Or you could just hijack the wire of the tank sender with a pocket.
That was what I was planning to use a digital fault. This would be a more elegant.
Probably,
The
yes,
guy was
because
doing it
all of
yesterday,
the things
getting everything you need out of it. Then start to
yes, typically.
It works faster.
get rid of this.
Crawl around.
It looked like an easy way of doing it.
It's greener. Use less code though.
You got everything on a bench working, connect it, start moving stuff, you just figure it out pretty easy. You can't change.
That's his strategy in the past. Get everything moving.
Too many clients?
Good job, Collin.